Good morning, everybody. It's welcome to this second day of the Winter School on Soft Robotics. And it's with my pleasure that I introduce you Professor Bram Vanderborght from the Free University of Brussels that will give us a review on variable stiffness actuators.
Thank you. Thank you for inviting me, and sorry I couldn't be here yesterday. We're working on a new humanoid project, fully compliant and learning and so on, and yesterday we had a meeting with a gynecologist about that, so that's why I couldn't be here. So I will talk about variable stiffness actuators. So I will start with stiff actuation very shortly. I think in the beginning it's a bit what you will probably know, but I don't know your background, so I will start with the basics. I will introduce series elasticity, parallel elasticity, and then Tom will tell you something about the efficiencies of electric motors, because that's often neglected. And then some novel concepts on series parallel elastic actuation and also self-healing actuators. So from our university, with 4 persons here, Tomislav, who is sitting there with his blue shirt, Raphael and Glenn couldn't make it yet. I think they're still in his bed. And then Tom, who will also present. So Tomislav is working on exoskeletons. You also will see some videos about. Raphael and Glenn are working on the series parallel elastic actuators. And Tom, you will see his work soon. So stiff actuators. So stiff actuation is in fact the oldest actuation because electric motors rotate with a very high speed but with low torque, and for our robots we want to have high torques and low speeds. So we need usually a reduction gearbox with a high reduction ratio, which makes the joints often non-backdrivable, and especially when we do position control, like in the industrial robots, for the typical applications, then we want to have precision, and then of course position control is the best. But usually that works best in known environments like industrial settings, but that makes the robots also very unsafe, and that's why you see that they're operated in cages. While for a lot of new applications, we want to go to unknown dynamic environments, and often including humans, and then those type of actuation is often insufficient, because we don't want the precision anymore, but we want more to go to safety, energy efficiency, robustness, force control, etc. And I think during this winter school, you will learn a lot about those. So stiff actuation has no energy storage. It's difficult to go to absorb shocks, and it's also often unsafe. So if you see Asimo, which is still one of the most advanced humanoid robots in the world, and I really like this robot, but when it walks, you see that it walks this kind of funny way. The reason is when the leg touches the ground, there will be huge impacts, and that impacts will damage the harmonic gears inside the activation system. So what the robot has to do, as soon as it touches the ground, he has to retract the leg in order to reduce this impact. That means that every time, after every hop, all his energy, his kinetic energy is lost. So for the next hop, he has to drain his batteries to inject again energy for the next hop. While when humans hop, we store energy in our muscle tendon system, like our Achilles tendon. So that means that very soon after running, Asimo doesn't have enough batteries anymore. Here you see some work when I was in Japan, I think in 2006, so a while ago, where I was a visiting researcher, and there we were stepping over obstacles. And then the problem was also there that we had to reduce the impact of the foot in order not to damage the harmonic gears of the robot. So that means that when you touch down, you have to brake the foot, so that consumes energy, so it has a soft landing otherwise you damage the robot. While as a human, you just go over it and you fall on the following feet and then you continue. And also when the robot falls or bumps into someone else, we have the advantage in Brussels that the headquarters for the shows in Europe and the Middle East is very close to our university, so I have the opportunity to regularly meet Asimo. But when he moves, you really have to be quite away from it, because if he moves his arm, you can really get hurt by it. So the robot has some torque sensors in the feet and in the hand, so you can do handshaking, then you do active compliance control, but you have to be careful with this robot due to its stiff actuation. So those are reasons to go from stiff actuation to actuation where there is an elastic element in it. And there are two approaches to have these elastic elements. One is by active compliance, where the compliant element is generated by software control. So this is this famous KUKA DLR lightweight robot, which is very impressive. So there the compliant behavior is done by a stiff actuator and then by software control with the necessary sensors. So the disadvantage here is that it's a limited bandwidth. So if you kick with a hammer on the robot, then you feel the hardware stiffness and not the stiffness set by the software control, because the impact is gone before the motors and the sensors can take the necessary actions. And also no energy can be stored, so it behaves compliant, but no energy can be stored. So to accelerate and decelerate, you need to consume energy. One of the big advantages that the control of stiffness and damping are just parameters, so that can go from very stiff to zero stiffness and the damping. And you can do it in different directions, so you have a lot of freedom to control it. And it's, I think, very robust, because now Mercedes is using this technology to assemble gearboxes for their cars, which they had a lot of problems when they were doing it with position-controlled robots, while he can do it in force control. So it's very nice. This was my PhD work. It's the biped Lucy. So this robot has not electrical motors, but pneumatic muscles. We will see a bit later about it. So because gas is compressible, you can have there the compliance in it. So there you have the stiffness in the hardware. So you have the passive compliance, and you can actually store energy in this. And you see here the compliant behavior of this robot. Because the muscles are actually quite strong, I could lift myself on the robot, so the muscles were strong enough to do so. One of the limitations of the robot, on the internet you see other movies of it, was that it's not possible to take the air fast enough out of the muscles, and that limits the walking speed of the robot. There are some other disadvantages as well. But we see that in a lot of biological systems, from cockroaches, different types of dogs, snakes, and insects, and so on, that this mechanism of energy conservation using springs is seen in all those animals to move, independent of the number of legs, posture, body shape, body mass, skeleton type, etc. And that inspired the robotics community to develop actuators with those compliant elements. And we were also, a lot of the project members of Safari were also in the project Actuators, which was very successful. And we have an overview video of it with the different technologies.
Variable impedance actuators, moving the robots of tomorrow. The capabilities of a human muscle have not yet been achieved by a mechanical device. An important missing aspect in classical stiff actuators is a passive element, like a spring, able to store energy and decouple inertias. Different variable stiffness actuators have been designed in the Actuators consortium, where output torque and output stiffness can be separately controlled. The different designs have different properties, such as low energy to change stiffness, large deflection range, high torque, or ease of building. Also, variable damping devices have been developed to facilitate their control. Compliant actuators allow exploiting the natural dynamics of a mechanical system, like for example bipedal walking robots. By properly exchanging kinetic and potential energy stored in a spring, energy-efficient robots can be obtained. By adapting the stiffness, different walking modes can be selected. As such, more human-like motions can be obtained. As for example, the Achilles tendon, which is a very important spring in the human body, can be imitated by using spring elements, obtaining much more efficient prosthesis. Also, to throw a ball, a stiff actuator cannot reach high speeds. The same motor can however store energy in the spring, so the ball can be thrown much further. This property is also required to kick a ball. Stiff joints fail in this task, while in a compliant actuator, energy can be accumulated to give a firm kick. Also, to absorb impacts, for example when stabilizing, the passive springs have an infinite bandwidth compared to a stabilizer using stiff actuators. Stiff actuators cannot absorb impacts, so hammering will break their gearboxes. By decoupling the actuator output from the gearbox by the springs, compliant actuators have no problem hitting the nail on the head. The adaptability of both the force and compliance allows a robot to increase its dynamic performance, for example for explosive motions like hammering. To interact with an unknown and dynamic changing environment, position control is not suitable. Force control over compliant actuators has much greater performances. The actuator allows for modifications of the imposed trajectory, for example to hold a cup or draw on irregular surfaces. By appropriately controlling the damping component of the VIA, the motion can be stabilized. Tasks with tools are unstable. We modeled and implemented the human strategy to learn impedance for stable and skillful interaction. Compliant actuators are also robust to perturbations and unpredictable model errors and changes, so compliant actuators can stay in the rhythm. So a fit stump is not a threat for the robot anymore, but VIAs become actuators you can trust. For rehabilitation devices, an accurate and adaptable force interaction and exchange with the user is requested. For human-friendly robots, safety is of primary importance. Also, in case of collision, a robot has to be resilient to self-damage. By decoupling inertias, safety can be improved. The impact energy of the collision is absorbed by the compliant element, so the critical components of the robot are conserved. This provides human-friendly robots, but please try to be gentle to the robot and not hit it with a baseball bat or by knocking it off. Compliant elements introduce oscillations, but damping control or passive damping actuators can compensate for those. For social robots that need to interact with children, safety is important, so the compliant actuators will play an important role. Compliance also contributes to a soft touch for a trustable human-robot interaction. This gives the robot the sweetness to live in synergy with them. Variable impedance actuators, moving the robots of tomorrow.
So within the Actuators consortium, and still this search for new actuators is going on, there were a lot of actuators developed, and as an output of the Actuators consortium, we also made an overview with the classification of those different types of actuators, because we saw that there is in fact not yet a winning actuator, but that for different applications you require different kind of actuators. So if you're interested, and I think this paper is on the website of this winter school, you find the overview paper. So the classification is on active impedance by control and inherent damping. I will not talk about this. I will more talk about inherent compliance, where you have one with a fixed stiffness, like the series elastic elements, and also the variable stiffness actuators, where a mechanical, so an extra motor, which increases, of course, the complexity of your actuator, is able to somehow change the stiffness, the mechanical stiffness of your system. And that is done by we saw three main categories, so spring preload, changing the transmission between the load and the spring, and the physical properties of the spring. So the most famous, and it's also the one that was biologically inspired, is the bi-articular antagonistic setup, where you have two muscles, like the biceps and the triceps in the human system. So there you have two motors, and one, it's easy to prove that you need to have nonlinear springs. And to build nonlinear springs, it's often not so easy, because from a commercial point of view, you buy usually linear springs, although you have also some designs of nonlinear springs. So you will see in the paper different designs to obtain from a linear spring a nonlinear behavior, while cam profiles and so on. And when you use pneumatic muscles, they have already, by their design, a nonlinear behavior. One of the disadvantages of this one is that you always need to tension with the two motors, the joint, to create stiffness. So we will see later that to generate torque by an electric motor, you continuously consume energy. So here you need to tension the two springs to just have stiffness at the output link and not yet have torque. And it's by having a force difference between the two that you will create here a torque. So that also means that maximum stiffness, so when the two motors extend the springs at the maximum, you cannot move the joint anymore because there you have the maximum stiffness. And so also the two motors have to be the same. So then Pizza and also DLR started to innovate on this, and they placed here an express thing, so you reduce that effect from here. And the advantage of this setup, and I think this is the setup used in the cubes you're using, is that to have maximum torque, you can let the two motors work in the same direction instead of having in the opposite direction, which means that the sum of the two torques is available at the output joint, which I think is a very smart solution, because at a certain moment, if you need maximum torque, you throw away the need to have adaptable compliance, and you can make the motor works to have full torque at the output.
Yeah.
So this is the stiffness control in the pneumatic muscles. So the pressure in both muscles you can rewrite, and you can give it a mean pressure and a pressure difference. So the mean pressure gives you the stiffness. So it's like in a biological system. When you relax both muscles, you have a very compliant joint. And when you stiffen both muscles, you have a very stiff joint. So you see it here when there is a high pressure in both muscles. The medium pressure is high, so you have a stiff joint. When you have a low pressure in both joints, you have a very compliant joint. And the pressure difference, so if you tension this joint and relax the other, you have torque in that direction, so your joints will move like that, and the opposite. Yeah. So you can both control the stiffness and the torque, which is a big difference with stiff actuators where you can only control the position. So for the antagonistic, then another possibility is to decouple the motors by different designs. So then you can have one mechanism to control, for example, the stiffness, and one motor to control the equilibrium position or the torque. And this is, for example, done in the Amask actuator of Jonathan Hurst. Another possibility is to go to preload adjustment by a single spring. And this is done, for example, in our Makepa actuator. So you see that you have one motor here with a lever arm that's connected to a spring. And when you bring it out of the equilibrium position, this spring will be extended. It will create a force. Due to the mechanism, it will create a torque, and it wants to bring it back to that position of the lever arm, which is the equilibrium position. So you see in all positions, the joint is compliant. And then by changing the pretension of the spring, so here it's fully pretensioned, now it's not pretensioned, so it's compliant, and when you increase the pretension, it becomes stiff. So you see here, the nonlinearity is in fact in this setup, so you can prove it by the equations, So you can use linear springs, and the advantage is that it's very easy to produce this actuator. Another advantage is that you can have different dimensions of the motor to control the equilibrium position of the torque, which is this one, or the motor for the pretension. So we will use it in exoskeletons, as you will see later. And in that exoskeleton, this one is a very big motor, and this one can be very small motors. So they can be designed separately. And then Sebastian Wolf from DLR, he inverted it, so we use extension springs, he used compression springs, and he used such a cam profile. And the advantage of using a cam profile is that you can shape the torque deflection curve, so you can design how your stiffness changes when you move the joint. And that inspired me to replace this lever arm by a cam profile, so you can design in the actuator the desired torque profile. So for example, for hopping robots, we want to have in the knee a stiffening behavior, because when you bend the knees, then the lever arm here, so this length increases. So then that means that your joint becomes more compliant while you want to have a linear legs behavior, and that you can design then by shaping this cam profile. Another possibility is changing the transmission ratio, which is done in the AWAS actuator. Also, Stefano Stramigioli from Twente designed such a mechanism. So you have here a joint, and you have here springs, and that can move. And you see, if you place your springs here, it's stiff. If you place your springs here, it becomes more compliant. And what you can do is you can work on one of the 3 points of it. So you can move the springs, or you can move these points. So here is the AWAS actuator from IIT. So you see here, it's compliant. Where is my cursor? So here it's compliant because the springs are very close to the rotation point, and then when you move those springs, it will become stiffer. So now you see it's very stiff. One of the big advantages of this type of actuator is that your force is in this direction, but you move the springs in the perpendicular position. That means to change the stiffness in the equilibrium position, you don't need any energy to do so because they're perpendicular. Of course, when it starts to move and it's out of the equilibrium position and you need then to move the springs, then you consume some energy. But that means that in this AWAS actuator, to control the stiffness, you can use a very small motor. While in the other designs, like this one, how you change the pretension by having the displacement of the spring parallel to the force. So to change here the stiffness, you in fact need you need energy to control here the stiffness. So that's the disadvantage of this type of actuator. On the other hand, you see here that the equilibrium position can be, the stiffness, the deflection of the joint can go over a very big angle. And so you see here that you can modify it over a very big angle, which is limited in this case because you see here, that's the range that can change the output link. So you see that depending on your requirements for your application, you can choose one of the different cases. So this one is not a lot of energy to change the stiffness, but the deflection range is more limited than in other designs. Then there are also some researchers working on changing the physical properties of a spring. So the bending stiffness, changing one of the parameters in it can change the stiffness of the joint. So Sugano, for example, changed the length of the spring, for example, by having those rollers. Thomas Sugar changed this inertia by rotating a beam in it, but the problem is here at the intermediate position you can have buckling. And the jack spring actuator modifies the number of used coils in a spring, so you change also the length of it. So for what are compliant actuators used? for safety, and Antonio Bicchi worked a lot on it, because and I think he will present more on it, because you can decouple the inertia. So if you have a collision with an object, with a stiff actuator, you will feel the complete stiffness in inertia of the complete system, while if you decouple with compliant joints, when you hit then the robot, then you will only feel the stiffness of that link and a portion of the next one, and so on. So you can reduce a lot those impacts. So this is an actuator we developed in our lab. Very recently, we have also a Baxter robot, and this Baxter robot has this series elastic actuators. We use it in a project with Audi. We have a factory of the A1 in Brussels, and there they have an aging workforce. So I think the average age is pretty high. So the problem is that they wanted to physically support the workers, but they don't want to replace them anymore. And that's why they want to investigate in those co-workers, where a worker can very easily teach the robot new behaviors without having to use a lot of math and programming skills. So here we programmed something that you teach the robot some components and you bring it to the desired position. And inside the wrist of the robot, there are cameras. So you see that it recognizes the piece and brings it to the end position. So the idea is by teaching by demonstration that you can easily teach the robot new behaviors. But you see, as a difference with the classical industrial stiff robot arms, there is no cage, so safety is very important. And here you can very easily interact with the robot, also because the robot is rather slow. So at the end of the video, you see the recognition of the pieces. So here you see the pieces being recognized, and then we can sort with it. In the future, we want to use in a project also 3D cameras to better position the robots. You also see that the precision is not that good, so it's a bit jerky, so we also want to solve that. Another robot we developed is for children, and then we want that the robot, Probo it's called, you have 20 motors in the head to show different facial expressions. And we want that the children are able to physically interact with the robot, so then of course safety is a primary concern, and we also want to give it a huggable appearance, not like a very stiff robot, but that you can hug the robot, so everything has to be made in soft materials and so on. So here you see this robot. So now we're having a European project. Here you see the cover. So now we have a European project to use it with psychologists in therapy with autistic children, because autistic children have problems with social interaction, and this is a social robot, and we want to use this robot to facilitate the therapies. One of the things is that not always the hardware, by using compliant actuators, is sufficient for safety. The reason is that in those compliant actuators, the spring element can actually store quite a lot of energy. And if you don't properly control that energy, it can create quite a lot of damage. And for example, if you block the arm and it stores energy in its spring and it's released, then it can have a very violent and explosive behavior, which we will use in some applications like prosthesis, in which I will show you a bit later some slides about it. So that's not always the case, that by compliance and a lightweight design, like this robotic arm, so it's compliant, it's lightweight, it can, we calculate it, break several bones in your face when you build up energy in the springs. So here you see a PID control with a step response, and you see it's a very violent behavior. Then you can say, okay, I will reduce the PID gains, but then the tracking performances, of course, reduce a lot. So the PID control, the maximum interaction force is 1,500 Newton, which is very dangerous, while we implemented the proxy-based sliding mode control So you see them at the maximum interaction force reduced a lot, and even the tracking precision improved. So how it works, so here you see the PID. So you have the target position, you have the link position, in between is the PID coupling, and you see the behavior with the PID coupling. So what we did in the proxy-based sliding mode controller is you don't only have the target and the link position, but you have also a proxy. Below a certain torque threshold, the target and the proxy are the same position, and you have this PID control, which can be tuned the same, but you can even increase those gains because it's kind of linearization of the system. So that's the reason why in the previous slide the tracking positions are improved. But as soon as you go over this torque limit, then the target and the proxy will move away, and then you will have a lambda, which determines the speed to which you return to that position. So that means, so here you have a high torque limit, and then a fast recovery speed, but you can also reduce the torque limit. So now with one finger, he can move it away, hold it like that, there is no torque buildup, and then it returns with that certain speed. And then you can also change with the lambda. So lambda now is 1 second, so you see that it very slowly goes back to the desired position. So by this kind of control, you control a bit the amount of energy in the springs that it doesn't build up, so that also by software you control the safety. This controller is used in our exoskeletons. Here you see the knee exoskeleton with pneumatic muscles. So this is zero torque mode to measure the walking behavior of this MS patient. She had a problem in the right knee. So the problem was that her swing phase was jerky. Also the left-right symmetry was not good, and she also walked with overstretched knee. And then we can apply new trajectories to improve that. And then we saw even after the interaction with the exoskeleton that the left-right symmetry was improved. And we used that proxy-based sliding mode controller for the safety reasons. Now we're building and finishing. It's already a process of years because it's an extremely complex machine, a full lower limb exoskeleton. Compared to its other exoskeletons, we also have ankle activation. We can support the full body weight of the user. And also there is the trunk can be controlled left and right so that the patient can feel stability and so on. So in this exoskeleton, we even, one of our researchers built very nice communication boards so that the whole system can be updated nearly at 1 milliseconds using both FlexRay and EtherCAT. This is, so the previous robot was a rehabilitation robot. This is an assistive exoskeleton. Here, the idea is, for example, for persons with functional muscle weakness, for example, if they have problems to lift off from a chair, that they get assistance up to 30%, so not yet full assistance. Now, our researchers are working on an exoskeleton in Biomod, like Tomislav, to give full assistance. And here you see again all those Makepa actuators, and this is built by VUB and programmed by KU Leuven in the MIRAD project. Apart from safety, also energy efficiency is studied. So here you see again that pendulum, and what we did is we measured the air mass consumption to do that motion, and we changed the stiffness. So we controlled the stiffness by controlling the mean pressure, and we controlled the frequency of the swing motion by controlling the torque of the motor, of the muscles, so by controlling the pressure difference. So if we did for every stiffness and for every frequency, we measured the air mass consumption, then we see that there is a clear value of minimal energy consumption. Why this happens? If you want to swing it at a certain frequency, and that frequency is equal to the unforced natural motion, then you don't need to use any energy consumption, only a little bit to overcome friction. So when you were hearing the experiments, then it was like psht, 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 psht. So every time the swing was getting a little kick to overcome friction, and it's like a child on a swing, the parent always gives a little kick at the end to keep that motion in that frequency. However, if you want to do the same motion and the natural motion, so by setting the stiffness is higher or lower, then the swing wants to go down, but you say, no, hold there, wait. So you continuously consume energy to fight against the natural motion. And then you see that you consume a lot more energy. So that's the reason why we want sometimes to have variable stiffness, although it's a more complex design, is that by changing the mechanical stiffness, you can tune it so that the desired motion almost equals the natural motion, because then you have the least energy consumption. And then we found a mathematical formulation for more complex trajectories to find the optimal stiffness, which is almost the average stiffness. So here we measured air mass consumption, so it's what you pay, it's what you consume. One of the problems of compressed air is that it's not very energy efficient to produce compressed air, and also it's very difficult to store. So that's why we moved to electric motors, because the energy from a battery is more easily to store. And then also I wrote papers about the energy consumption of compliant actuators, but I studied up to the output shaft, so the mechanical power, so torques and speeds. And then we said generally in the community, yeah, electric motors have a high energy efficiency, which is true, but it's only at nominal working conditions. Away from that nominal conditions, the energy efficiency very quickly drops. So in fact, you should include in the study of the energy consumption also the motor, and about that, Tom will present you his research. So I will give the word to Tom.
Thank you, Bram. Yeah, it's all on this. Okay, it's a bit difficult with all the cables. Okay. Okay. So I'm Tom. I'm also working at the University of Brussels in the Department of Bram. And, well, I think he already did my introduction, more or less. So I will have a small talk about the energy efficiency of actuators with DC motors. Now, before we move on to their efficiency in a compliant setup, let's first try to understand why these stiff actuators are not so energy efficient. Well, this is the typical topology of a stiff actuator. So we have the three components. It's actually a servo motor, so it has the controller, the motor, and the transmission. I already had a talk about this yesterday. So what it does is essentially it connects the power source, which is an electrical source of power, to the loads, to which we will impose. Sorry? Okay, yeah. To which we will impose a motion, and which will lead to an imposed power profile. So what happens? Well, usually in most applications, we have power flowing from the power source to the loads. So this is a positive power, because power is the product of force and speed. So, for instance, when you're lifting a load against gravity, that means that we have force. Well, the motor is applying a force, an upward force, And the speed is also upward, so it means product of both is positive, so positive power, motor is driving the load. So in this case, what we have is that while this power is flowing through all the components, we have losses because each of the components has its own efficiency. And so in this way, we see that 40% of the power that we use as input from the power source is lost through all these components, and we only have 60% left at the load. Okay, so this is in most applications at constant load and constant speed, but in robotics, there is something special. We don't have these constant loads and constant speeds, and typically we also have cyclic motions. And in these cyclic motions, we also have negative power. For instance, as I said, lifting a load is positive power, but if we lower it again, the force is still applied in the upward direction if the lowering is controlled, but the speed of the motor is now reversed. So the product of both is negative. And negative power, what it means is that we in fact have power flowing from the load to the power source. Now in this process, again, we will traverse or we will pass through all these components with their efficiencies, and we will again accumulate all these losses, which is obviously not a very energy efficient process if we constantly cycle through all these components and their losses. So how can we improve this? Well, the solution is very simple. Try to find a way in which we can bypass all these components so we don't have to pass there with all our power. And how can we do this? Well, quite simple. We can introduce an energy storage buffer at the output. And this is typically an elastic element. Essentially, we have two basic choices. We can do this in a series configuration, or we can do this in a parallel configuration, like this. So what happens when we do this? Well, suppose that we have some negative power available at the load. This will attempt to move towards the power source, but it will pass through the elastic element, or some of this power will pass through the elastic element in a parallel configuration. Now this elastic element allows to store this power until energy is required from the load, positive power is required, and at that point it's able to release this energy again. So essentially what we will have is that, okay, strange, that energy is cycled in between the elastic element and the load. And this energy no longer has to pass through all these components here with all their losses. We only experience the hysteresis loss of the elastic element. This is a lot smaller than the typical efficiencies of the motor, transmission, and to a lesser extent the controller. So this is exactly the gain that we have with these compliant architectures. Now the choice between a parallel or a series architecture is actually a choice that we usually don't make from an energy efficiency perspective. The performance is usually the thing that will define our decision here. And one thing that's quite important is obviously the safety. So as we've mentioned a few times before, a series architecture takes care of a decoupling of the motor and the load, which increases safety. But in the parallel architecture, the load is still rigidly coupled to the output shaft. So we don't have this increased safety in this architecture. And in fact, we cannot really call it a compliant actuator for this reason. It's still stiff. But because it's still stiff, it's still very well suited for accurate position control. Series elastic architecture is a bit less accurate in position control usually. But on the other hand, is well suited for force control because essentially the force on the load and the force on the motor are still the same. Now, looking at energy efficiency, there are two interesting properties, or is one interesting property. That is the extra anti-resonance frequency that we have for the series elastic actuator. Anti-resonance means that the output can oscillate at this frequency, but the motor will not have any speed. On the other hand, in the parallel configuration, we only have the resonance frequency, actually just like in a stiff actuator. And resonance frequency means that the load can move, again, oscillate at this frequency without a torque from the inputs, so the motor. So this means that the latter architecture allows for a reduction of motor torque, while the first allows for a reduction of motor speeds. And this is basically the idea that will make these architectures more energy efficient and will also allow for a higher peak power output. Now, the efficiency has already been studied in a series of papers by Martin Kremer. And, well, in these papers, the plot we see here, they studied peak power, which we have here, and the energy requirements of the actuator. And they did this for different running and walking speeds. They looked at the ankle joints, and they measured the consumption there. They did this for different architectures. They had the direct drive, which is well, essentially a servo motor, the parallel elastic actuator, series elastic actuator, and a combination of both, which is a bit less interesting to us. Okay. Thank you. Now, looking at peak power, we can clearly see that the peak power that is required from the motor is significantly decreased for the parallel and the series architecture. Energy consumption, well, there the difference is not that clear. In many cases it is reduced. In some cases it seems it is not. But I will not go into too much detail here because I actually have one fundamental remark about this paper. And that is the way the energy consumption is calculated. It's calculated by taking the integral of the absolute value of the load. Now, I mean, there are several approaches in literature. Some authors use the absolute value, some don't. Personally, I don't think using the absolute value is a really good way of calculating the energy consumption, but this is a separate discussion which I think would lead us too far here. But what I do want to talk about is the fact that these authors measure the energy consumption at the output side. So this means that they don't take the speeds and load-dependent losses into account. And there are, in fact, quite a lot of speed and load-dependent losses in gearboxes and motors. For instance, this is the efficiency of a spur gear for various torques. And what we can see here is that at low torques, the efficiency quite rapidly falls down. This is even worse for gearboxes, which are composed of multiple spur gears, obviously. There's also some dependency on speed, as you can see here. The plot is at different speeds, and as speed increases, efficiency decreases. But this decrease is less pronounced than decrease with torque. Motor efficiency is actually quite interesting to study. So I made a DC motor efficiency map here, which shows motor speed on this axis, motor torque on this axis, both for negative and positive speeds and torques, so that we have the 4 quadrants here. Quadrants 1 and 3 correspond to positive power, so that is motor is driving the load. Quadrants 2 and 4 correspond to negative power, so that means that the load is driving the motor. Now, we can see a few interesting things in this plot, which is, by the way, calculated by taking the product of the voltage and the current, obviously. And essentially, that means that we will have 2 types of losses. We have, on one hand, the resistive losses due to the winding resistance. And on the other hand, we have this term, which contains all the other losses in the motor, such as bearing friction, friction to the brushes. And we model this as a speed-dependent component. Actually, this component makes sure that the no-load current is consumed at no-load speed. And this term, well, this actually contains all the losses which we have when there is no speed at the output, but when there is torque. So this also means that at no speed at the output, but if we have a torque, that we will still consume some current and some power from the power source. So this is an important remark, which I will also come back to in later slides. So as I said, quite a few interesting things we can see in this efficiency map. First of all, we see that there is only maximum efficiency at low torques and relatively high speeds. And we also see that there is a huge difference between the positive power regions and the negative power regions. The most striking difference is here, this very dark blue zone in the negative power region, which I like to call the zero efficiency region, because a very strange phenomenon is occurring here. As we are in the negative power region, we know that there is some energy available from the load, which can be transferred to the power source. But the problem here is that the losses, due to the resistance, due to damping, are higher than the energy that we have available at the load. So this means that we will still draw power from the power source to compensate for these losses. So essentially, the actuator is receiving power from both the outputs and from the battery. This is not the case in the rest of this region, where we actually have some energy available at the load, which we can store back in the batteries. And proof for this can, for instance, be found in papers by, I think, Sang-Bai Kim, who was working on the quadruped robots, and he did some measurements to actually prove that some energy can be regenerated by the actuator he made. Okay, so if that doesn't convince you that there are some load and speed dependent losses, then I can maybe prove it to you by demonstrating a few measurements that I made in our lab. So I did these measurements on a pendulum setup. Pendulum is here, where I imposed a sinusoidal trajectory to the output. The mechanical power is more or less sinusoidal, so measured at the output. But the electrical power, which I measured at the battery terminals, is clearly very different from the mechanical power. It's more or less distorted, and it's, well, basically of a much larger amplitude. And this is exactly due to the speed and load-dependent losses. I will also show a small example calculation. So what happens if you don't take load and speed dependency into account, and if you use the absolute value, as I mentioned earlier? Well, essentially you get a huge overestimation of energy consumption. If you compare this to the energy consumptions I measured, it's a lot larger. On the other hand, if you take a more accurate model, such as the one that I'm proposing in my papers, just promoting my work here, you can see that you're actually able to predict the energy consumption quite accurately. So this shows that these load and speed dependent losses are actually quite important in actuator systems. So what about the variable stiffness actuators then? Well, I haven't done any measurements yet, but I can show you a theoretical study on the same pendulum setup, so the same idea, imposing a sinusoidal trajectory to the output. And what this shows us is essentially the resonance and the anti-resonance frequencies. You can see these in the power plots. And for a series configuration, we have two resonance frequencies, actually. One of them is here. The others you don't see at high amplitudes of the sine, so this is why you don't see it at this plot. The second one is in fact the anti-resonance frequency, which I talked about. And the interesting thing about this is that it's very much dependent on stiffness, which you can see here. The frequency of the pendulum is here, peak power consumption here. And this dependency on stiffness is what we can exploit in variable stiffness actuators to increase the energy consumption. Because as you can see, energy consumption, well, peak power is quite low. And when we translate this to energy consumption, you also see that obviously we have lowest energy consumption in this region. Now, there is a small remark that I need to make. When we look at the electrical energy consumption, mechanically, electrical consumption is 0 because the output speed is 0. But electrically, we still have some losses, as I mentioned before. So if we simplify the electrical power consumption at the motor, we see that we still have this term left, which is proportional to the resistance and to torque squared. So we'll still consume some power. The parallel elastic actuator does not introduce this anti-resonance frequency. It does also not introduce a second resonance frequency. But what it does do is it shifts the resonance frequency that we have for stiff actuators in such a way that it is dependent on stiffness again. So again, we can control this by means of a variable stiffness actuator. And again, here we prove that we have minimum energy consumption at this resonance frequency. And this time, we still have some losses, but the losses that we have at the motor are damping losses. And these are actually usually smaller than the ones that we have due to the winding resistance. So from an electrical perspective, the parallel architecture is actually slightly more interesting. So the conclusion of this small presentation was that there is indeed a load and speed dependency of the motor and the gearbox losses, and it cannot be neglected in our calculations. And when we look at the parallel and a series topology from an energy efficiency perspective, we see that in the series configuration, we will be exploiting the anti-resonance frequency, whereas in a parallel configuration, we'll be exploiting the resonance frequency. This means that in the second case, we'll reduce motor torque, which means that we still have the damping or the friction losses, which will be dominating. In the series architecture, we'll reduce motor speed, which means that we will still maintain the resistive losses. And since the latter are more important than the former, we can say that we can expect series elastic actuators to be electrically less efficient at anti-resonance than their parallel counterparts at resonance. And this is the conclusion that I can draw from these simulations. Thank you very much.
Een beetje om moeten over. Je mocht het uit.
Okay.
So, this exploitation of the natural dynamics is in bipedal walking robots. You have those passive walkers, and by tuning very smartly the dynamics of your system, you can walk without any energy consumption. If you walk down a slope, to walk on level ground, you need a minimum of actuation. The issue is that when you have a fixed stiffness, you cannot change the walking speed and the step lengths, for example. But if you have variable stiffness actuators, you can modify them. So that means that with small steps, and then at a certain moment you change the stiffnesses, you can walk with bigger steps. So that's also where you can exploit the natural dynamics by variable stiffness actuators. Another application is explosive motions, and we use that in prosthesis. So walking with classical prosthesis is like walking with closed keyboards. It goes slower, you consume more energy consumption, and usually you have also an asymmetric gait. So you know, in a normal ankle, you have initial contact where you have heel strike, then you have flat foot, then you have go to maximum dorsiflexion where you have heel off, and then you go to toe off. While when we measure on a classical prosthesis, it's like a very small spring, so you see from 0 to 15 degrees, it's something like that. and you only have damping, hysteresis, so you lose energy, while a sound human ankle injects quite a lot of energy. So one of the things we can do one of the things is that for a sound human ankle, the problem is that we need about 250 watts and 120 Newton meter. And if you want to do that with a classical electrical stiff motor, you need a huge motor, which is so heavy that the rest of your body will consume so much energy to make your foot swing to the back and the front. So there is no advantage of using powered prosthesis. So the idea should be to reduce a lot the power requirements and the size of the motor. And there are a number of approaches to do so. One possibility is, if you have here this one, the amount of the area under this curve is the amount of energy that can be stored in a spring. And in a stiff setup, you lose that energy because you need to brake, like Tom explained, and then to re-inject that energy with all the losses. While if you can store that energy in a spring and release it, you can reduce this power peak. So this is the power. So you see that here you have negative power. So you dissipate energy, but it's smarter to store that energy. And then you can reduce this peak so you don't need such a high powerful motor. The second, and that's how, for example, the prosthesis of Thomas Sugar and Johor work, something like that. Another approach we took is, instead of using a motor during a very short time with a high power peak, is to reduce a much smaller power motor, but during a much longer time. So this area under this peak is spread out over a longer period, but with a lower power. So that means that we need something to store energy and release it, and it's a bit the same concept like throwing an arrow, or you can do it with a lot of power. Smarter is to use a bow and to gradually store energy in that bow. You lock it, and then you release it, and then suddenly all this energy is injected. So you have a very explosive motion. So you see, compliant actuators can be very explosive. That is dangerous, but here it's requested. So what we do here is that you have two springs. One spring here, from heel strike to foot flat, stores energy, and then goes back and then stores energy in it. And then, in the meantime, a motor is pulling on a spring, so it's storing energy in the spring, but this lever arm is locked with this leg, so the ankle doesn't see that energy. So it's just like the arrow and the bow, storing energy. And at heel off, which you can detect with a foot switch, then all this energy is injected, so you have a jump in energy, and both the energy from this spring and this spring is released in your ankle joint, and you have a powerful push-off. So this idea is used in M-Foot 2. So it's treadwheel walking at 5 kilometers an hour, which is already much faster than normal walking. So here you see that this energy to go to maximum dorsiflexion is stored in a spring, and in the second time, also energy is stored in the spring by a motor. And at heel off, here you see a locking mechanism being released, and all this energy is stored in the spring, released from the spring. One of the things here is that you don't use this amount of energy, which is shown here. So in the M-Foot 3, we have an extra locking, and if you're interested, you can read the papers, so that we can also store this extra amount of energy, but then you need an extra locking at this point. So here you see the latest version of the M-Foot. So one of the difficulties is that you need to store quite a lot of energy at a high force, and then you need locking mechanisms. And here we used a singular position to lock it, but I will explain you a bit later. So here you see the person walking with it. At the moment, we control the amount of energy by measuring the step length, but we want to go to more advanced gait detection algorithms. For example, if you walk uphill or downhill, then the prosthesis would give the same amount of energy, while walking downhill you need less energy, and walking uphill per step you need more energy. So we still need to develop those kind of gait detection algorithms. The Pierre Chirel, who developed this prosthesis, is now working in a project to go with this to a commercial application. Then we have another project, Cyberlex. It's a European project, and there we're building a knee-ankle prosthesis. So as before, the ankle requires a lot of energy, so we can reduce that power requirement by storing some energy. While if we see to the knee, then mostly the knee is a dissipative joint. So the muscles mostly have to dissipate energy, because you see it's mostly negative power here. So what was our idea? Why we don't use that energy and transport it to the ankle to reduce there the power requirements. But you see that when it's available, it's not required by the ankle, so you need to store energy, to lock the energy, and so on. So this is a project together with PISA, and here you see the exoskeleton. So the torque angle of a knee this is the stance phase. So you see during the stance phase, it's a stiff joint. During the swing phase, it's a very compliant joint, and that's the reason why those passive walkers in stance phase often they have a lock position in the singular position for the swing phase, and during the stance phase and during the swing phase, they often make it completely compliant. So when you move the upper leg to the front, the lower limb will automatically bend for enough foot clearance, and then before you reach you need to go again to a stretched position, but then the lower limb will crash into your joint, and to prevent that, you need to break it, and that amount of energy can be stored to bring it to the ankle joint. So you see that locking is in fact important, and we see that in recent years the number of locking mechanisms increased a lot in robotics, although locking mechanisms are already very old and described in old mechanical books. But when you need to store energy, you can do it in a spring, but when you want to keep it there, you need to really lock it, and then you can use a number of devices to do that. And if you're interested in the Robotics and Automation magazine of March, there will be a review paper of different locking mechanisms, because the same as with the variable stiffness actuators, all of them have advantages and disadvantages. So we have 3 major groups with mechanical locking devices, like ratchets and so on, where you have a mechanical blockage. You have also a lot of friction devices, and you have also the singularity locks. And that is, for example, very useful when you want to look at the high force. So you see here that you have a singular position, so you can store a very high force, lock there a very high force, and by pushing here with a little force, you can bring it out of that singular position, and that's then the energy stored, for example, in the spring, like in the amp foot, is then released. The disadvantage of such a mechanism is that you can only lock it in one position, while, for example, for a frictionless mechanism, you can lock it in any position, and here, for example, only in a discrete number of positions. So all of them have advantages and disadvantages. So we also made a flow chart how you can choose your locking device. And you see a lot of different applications: manipulators, prostheses, leg robots, fingers, reconfigurable robots, and another type of robots are using locking mechanisms. And you see different locking mechanisms are used for different types of applications. I will now go to another part of my presentation. Which is about series parallel elastic actuation. So one of the things is, for example, and also Tom already mentioned it, this is a stiff actuator, so all the forces and all the powers have to be delivered by the motor. While if you use a compliant element in series, then the energy requirements reduce because energy from the environment can be stored in the spring and released back, so it doesn't have to be delivered by the motor, so you can reduce the power requirements. One of the problems here, and when you have variable stiffness actuators, you can change the stiffness. One of the problems is that all the force or all the torque when you have a rotational joint goes through the spring, but is also felt by the motor, which is a problem because, for example, if you want to have a disposition of your robot, then all the force is still felt by the motor. So although your mechanical power is zero, because you have no speed, but you still have a torque to be, the mechanical power is zero, but not your electrical power, because the motor has to deliver a torque, so it has to consume current to maintain that position. So that means at that moment, the energy efficiency of your robot is zero. So your motors will heat up without any output motion. So we use, for example, also now with our children with autism, but if we use a robot a long time, then it will get overheated, even sometimes if it doesn't do a lot. Moreover, the size of electric motors and gearboxes is in fact proportional to the required torque. So for example, for jumping, for exoskeletons, you still need a lot of torque, and variable stiffness actuators will not reduce that torque, so you still need often very big motors. Moreover, the copper losses in an electric motor are proportional to the torque to the second order, or also torque is proportional to current, so you see high torques lead to high losses like Tom explained. So I think the challenge, compliance were able to reduce the power requirements, but not the torque. So I think many actuators are not yet there to work energy efficient, provide enough torque, so different applications will still have difficulties, like for example in our exoskeletons, they have lightweight motors to deliver enough torque to give assistance to a human. So I think the challenge is to improve the torque-mass ratio and improve the energy efficiency. And then there is an interesting observation that the biological muscle, there the power density is 10 times lower than the power density of an electric motor. Also, the maximum efficiency of a biological muscle is much lower than the maximum efficiency of an electric motor. So I don't think we need to throw away the electric motor. I think we need to continue to investigate how we can transmit the power of an electric motor to the output shaft to make that efficient. So that's the work of Glenn, Raphael, and Tom, and so on, and other members in our group. So already Tom mentioned parallel elastic actuation. So for example, in such a desktop lamp, there are no actuators, but you can position the lamp in any position, and when you release it, due to friction, of course, but also due to the parallel springs, parallel to the joints, it will stay in that position. What's the problem here? If you change the load, then that mechanism will not work completely anymore, because it's the settings of those springs are made for that specific load. We also use such a gravity compensation mechanism. You saw the video of the exoskeleton Knexo. We don't want that the user feels that weight on his legs. So that's why we made a gravity compensation mechanism for that exoskeleton. But that also means if you have a different exoskeleton, different loads, it will not work anymore. That also parallel spring is used, for example, in the prosthesis of your But there the advantage is that you have a certain profile to walk, so you can design it for that profile. Also here, for example, the work of Metin, you have a pendulum, and that is the torque required to make that swing with a certain trajectory. But if you use a parallel spring, you can reduce the maximum torque requirements. The problem is here, if you want to have another trajectory, then you need another torque profile, and maybe then your parallel springs will work against what you want to have. So maybe you heard already of the Hill 3 types element model to have a model of your biological muscles. You have a contract element, which is a motor, a series element, and a parallel element, and different researchers used 1, 2, or 3 elements of this model. But we want to move beyond this by going to series parallel elastic actuation. So again, in a stiff setup, a series elastic actuator or a variable stiffness actuator, when we have a force, all this force is felt by a motor. So what we want to do if we have a force, that this force goes not only through the motor, but is taken by a lot of parallel springs. And because you have only one motor in series with one spring, the motor only feels a fraction of the complete output force. What's then the problem? That you need to have a mechanism which makes the motor kind of jump between the different springs so that you can bring the springs from an unpretensioned phase to a pretensioned phase. So you need to have, when, for example, you need to lift the load, you can do it with one spring, so you can lift it. Maybe a better solution is you have 4 springs, for example, and one by one, you bring the springs up, so then every time you only feel 1/4 of the total force of that spring. And all the other forces go parallel to the motor, so the motor doesn't feel it. Another thing we want to do to investigate is, if you have multiple parallel springs, every time you use a motor, but a non-back drivable element or a brake, so that when the motor doesn't move, it just brakes and the motor doesn't feel this force. So where we got the concept is, in fact, when we lift something light, we have a lot of parallel and series muscle fibers. When we lift something light, we only use a few muscle fibers. When we lift a heavy table, then we use a lot of muscle fibers. And this is called variable recruitment, and we wanted to investigate that concept also for actuators. And this is, in fact, our ERC grant, the topic of it. So we made a first proof of concept. So you see, you have here one single motor, and one, by a mechanism, all the springs are tensioned. So here you will see a view from the top. So you see you have 4 parallel springs, and one by one, the springs are moved from one position to the other position. The advantage is, it's a very small motor, it's a very cheap servo motor, it can lift a very heavy weight, and we can even switch off the power, and the load stays in that position. So normally with a normal series elastic actuator or a stiff actuators, due to the weight of the load will go down again, but here the motor doesn't feel at that position the load anymore, so you can switch it off, it's not required anymore, and it maintains that position. So how we do that mechanism to have this locking and switching to the next state, that is in fact by a Geneva mechanism. So you see what you want to have is a continuous rotation of the motor and a discontinuous motion at the output shaft. And when it doesn't move, it has to be locked, and which is done by this profile. The problem here is that you have the transmission ratio, because of this link, moves in and out. So the ratio changes. We use mutilated gears. So here you see that in this position it's locked, and from here to here, the motor will feel this output torque and will bring it from this singular position to that singular position. If we then measure the torque, so the black one is the torque needed in a stiff setup to bring a load from this position to that position. If we use a series elastic actuator, we need to bring it from here, so there it's a singular position, so it feels no torque, and it's also hanging down, so the load has no torque. And you bring it to the other singular position, so you go to maximum torque, and then you drop to 0. And you see that torque is about the same. If you, however, use 4 parallel springs every time with this mechanism, then you see first hub, second, third, and fourth. So the maximum torque the motor feels is much lower than the maximum torque here. Where is then the torque gone? Well, it's taken by the parallel springs. So the yellow line are the parallel springs. So you see every time they take a large part of the torque, and the motor only needs to give a fraction depending on the number of parallel springs of this torque. So if you then have a look to the power consumption, so what we did here, we moved the joint to that position, and when we moved it like that, in a stiff setup, that's the power consumption. When you use 2 springs in parallel, it goes down, and when you use 4 springs in parallel, it's 11% in comparison with a stiff setup. What's the reason? The output power is the output torque multiplied by the speed, but the big part of the torque is already taken by the parallel springs. So a big part of the torque is taken by the parallel springs where there is no motor visible, and only to move it up and down, that torque has to be given by the motor, which also means probably that your motor is used at a more energy efficient region. The reason is, in our robots, we want to have very small motors because they're light, but that means that we want to get the most out of this motor, so we use it very close to the stall torque. But close to the stall torque is a very energy inefficient region, because where is the optimal energy efficiency of the motor is at about 1/7 of the stall torque, so at low torques. So here we reduce a lot the torque going through the motor, so we let the motor work at higher energy efficiencies. So it's very important when you want to study energy efficiency, also like Tom explained, to not only look to the mechanical output, but also include the properties of your electric motor. Because for a pump, it works at nominal conditions, so then it works, you can design it that it works very energy efficient. But in robotics, we work at varying loads and speeds, so we use the whole region of that motor, and in a lot of regions, like Tom showed, you have a low energy efficiency of that motor. So of this first SPA, we saw that we can reduce the torque and also the energy efficiency, but we still kept that compliance. Where the points to improve mechanical complexity, I will discuss a bit this at the very end, at the conclusions. We also had only unidirectional torque, so it could only pull but not push, and no variable stiffness. So in the next design, we used again our Makepa actuator. So one motor controls the equilibrium position, one motor controls the stiffness. And what we did is we stacked several Makepa actuators on top of each other. So that you see here, so we have 4 parallel springs, so stacked on top of each other. And we have that lever arm which controls that spring, like in the previous slide. But what we want to do now is that in the extreme positions of the Makepa, so left and right, we will lock this tensioner. So that means that then the lever arm can continue to rotate, and so the Makepa actuators deliver a torque, but it's not felt by the motor. And then we can do it defaced by 90 degrees, so that every time one of the layers is engaged with the motor, but the total torque which is felt at the output link, the motor feels only 1/4 of this output torque. So here you see a video of the working principle. So you see here the 4 lever arms, so you can Now there is no power consumption because we just switched off the power, and you can see you can apply a torque on it and nothing happens. And here you see the lever arms one by one bring the springs one outer position to the other outer position. And every time in the outer positions, you lock the tensioner. So that means that if you have a load on it, you can move it, and the motor current stays very low because every time the motor engages another spring. Here we use still servo motors, so we also wanted to go to higher loads. Moreover, the problem here is that you have a fixed output shaft with the lever arms connected, so that means we can only have 4 layers because after 360 degrees the lever arm is again there and it cannot move the tensioner anymore. So what we wanted to do is to go to multiple layers, so 8 layers or even maybe more, because the more layers, the more we can reduce the torque. So then we need a mechanism to go every time the motor from one layer to the other, and that we used with a cam-based design. So here you see a mechanism that has 2 phases, an actuation phase and a travel phase. And when there is one travel phase, the other is in the actuation phase. So the idea is that in this phase, you bring the lever arm, the tensioner, from one position to the other. If it's in the extreme position, you go to the travel phase, so you go to the next layer to engage the springs there. So you can move it from one position to the other. If it's in one of the 2 positions you want, the cam will automatically go to the next position. And then you can have multiple of those devices, so you can even have overlap. So here you see that one by one you can control all the springs. So here you see that a very heavy weight can be controlled by a very small motor. So if I go back, so here you see the very small motor that can deliver huge torques. And the advantage, you can also say, okay, maybe we use a very big reduction ratio, but then you cannot do the load cancellation. You cannot switch the motor off and still provide that torque, which is possible in this case. Another thing, and that's together with Antonio Bicchi and Professor Schultz, he's now in Tuzla, is to use a lot of parallel springs, and every time with an actuator. So here you see that with a lot of parallel springs. One of the things we need to improve here is to have the locking device, because here you use coils, and with tension the spring, to maintain that position you need to continuous to provide current to do that. So in the next design we want to include lockings so that you bring it to one state to the other state, and in between you don't need to consume energy. Then the last part of the presentation, I want to introduce self-healing robotics, which is a bit futuristic. So the idea is when a human falls, we break something or we have a cut, and then we have an amazing property in our human body that our body can self-heal. While in robotics, we need to over-dimension our robots, because if the robot falls, then we don't want that the robot is broken. So usually it leads to heavy designs of robots. Moreover, by using all those compliant elements, and even if you go to soft robotics where they use rubbers to build complete robots for unknown dynamic environments, but there you can encounter sharp objects, so you can have a cut and then the robot doesn't work anymore. So self-healing materials is in fact a hot topic in the material sciences, and you can already buy from Nissan a car, and when you have scratches on your car, you place it in the sun, and in Italy you have a lot of sun, and I think when I see the parking behavior here, you can also have a lot of scratches on your car. And you place it in the sun, and then a self-healing mechanism starts so the scratches are closed again and you don't have scratches anymore. Also in the Netherlands, you have now a road, and when there is a crack in the road, then a self-healing mechanism starts, so the crack is closed again. So the idea is that you don't need to do so many roadworks anymore because the road has self-healing properties. And also KLM is testing with engines where some parts have self-healing properties. And what we want to do is to bring this to robotics, so when a robot falls, gets a damage, that he can heal himself. There are actually quite some materials under development in the material sciences with this property, and some are autonomous, so that means that when the damage occurs, then he doesn't need an external stimuli to heal himself. You have also non-autonomous systems where you need, for example, heat, light, or chemical stimuli in order to start the self-healing cycle. So the autonomous systems are the most interesting. The problem is you have, for example, encapsulations, for example, in those roads. So you have a capsule with an element in it, and when it breaks, the chemical substance comes free and starts the self-healing process. The problem is you can do it once, but then the capsule is broken, and when you break it again, it's not available anymore, so it can only work one time. While for robotics, we want materials that can do it infinite number of times. So then, moreover, for robotics, we need mechanical properties like stiffness and damping that we want to tune. So when we did the investigation, we saw that only the Diels-Alder bonds are interesting. Moreover, they need a heat stimuli which is below 120 degrees of Celsius, which is still okay. So here you see a video of a cut. It's 520 times faster, and you see after a while, by the self-healing, the cut closes. So at low temperatures, you have a solid network structure. By heating, you increase the mobility of the different chains. So that means that you can close the gap by the mobility, and then you cool down, and then your cut is healed. One of the very interesting properties of this material is that you can change the mechanical properties by changing the length of those chains. So if we do then measure the mechanical properties, when we have very short polymer chains, then we have a very brittle material. So that means that you have a very hard, brittle material. While if we increase the polymer chains to a longer length, then we can achieve very elastic, so we can have elastic behavior, even with very high strain at maximum at fractures. What's even more interesting is that we can mix, because it's the same material, we can, if you want an intermediate property, then we can mix G400 with G2000, so we can really tune the mechanical properties of this material. So we developed with this material two concepts. One is a self-healing fuse. So the idea is if you have a serious elastic element or even maybe a stiff actuator, when there is an overload, or your gearbox or your motor or your elastic element will be damaged. The idea is if you have an overload, the fuse breaks, so the danger is gone, then the joint is broken, but you bring then the joint back, the fuse two parts back to each other, you start a self-healing cycle, and you can work again. Why is this often an advantage, maybe? Because your robots are very complex, and to change a part, you need to disassemble the whole day your robot to fix it, and then to reassemble it again, and then it's working again. While here, maybe you can have, and as I said in the beginning, it's of course a bit futuristic, that you break, it starts a self-healing process, so you don't need to disassemble, you don't need, as a customer, to bring it back to the robot shop, for example, and so on. So what we did is here, this is this material, and then you have here a reduction in diameter, so we're sure that it will break here. And then we did some tests, so we healed the parts together, then we break it in a universal testing machine, we measure the maximum force, we bring it again in, we self-heal it again, we break it again, and so on. And you see that the mechanical properties don't go down. While all those differences, at the moment we make it by hand, and it's quite difficult to have the correct diameter. But the concept, I think, is working, that we can have materials in robotics with self-healing properties. A second topic we worked on are soft pneumatic actuators. So you have those actuators, those soft robots, like we have like little grippers, fingers, crawling robots, and so on, based completely off rubber. So, but when they encounter a sharp object, they have a cut, and then it doesn't work, of course, anymore. So our concept is to make this from self-healing material. So one of the things to have this kind of behavior is that you need an anisotropy in your material. This material needs to be stiffer than this material to have this bending motion. But we saw a few slides that we can change the stiffness of this material by changing the polymer chain length. So that means that this part will be of G low number in G series, while this one, we want a very compliant one, so we need very long polymer chains. So here you see we made a cube, and so you see that this consists of several cubes. So at the moment, we made only one cube because to make this material in big quantities is not yet so straightforward. So this one is a compliant material, and this is a stiff one. One of the problems of these materials is that it's not possible to mold them. So those ones, you can mold them in a certain form, which you, for example, can 3D print, but it's not possible by this material. So what we used is we used the self-healing property as the fabrication process of this material. So what we did is, Seppe Terrein did it. He made from a sheet a cross, then he folded it together, and then he used the self-healing property to not glue, because there is no glue, but to connect the sides of each other. And then we used the self-healing property to connect the lower plate on it. So the fabrication process of this material, to make a certain shape of it, we also use the self-healing property. And then we can inflate it and deflate it, and it generates this forces and form deformations which are similar to the devices described in literature. So that means that we can make also those fingers from this type of materials. What we did then, we made a cut in the material. So with a scalpel, we made a cut. Then we started by heat the self-healing process, and then we measured again, and you see that we have, again, exactly the same properties. So that means by this material, we have a proof of concept that self-healing materials maybe can work also in robotics. So as a conclusion, we presented compliant actuators and different applications for safety, energy efficiency, robustness, and explosive motions. But the requirements for the torque, mass, and efficiency are not yet reached, and that's why several applications like power augmentation, running robots, manipulators, exoskeletons still require more advanced actuators. So then we introduced the switchable parallel and series elastic elements, and we showed on proof of concepts that we can improve the torque and also improve the energy efficiency. And this is an idea that we still need to develop further, and that's why we have the ERC grant. Then I want to make a comment on the mechanical complexity. Of course, the problem is that the mechanical complexity of these devices increases a lot. But I think by new advanced manufacturing processes like 3D printing and so on, this maybe will become possible. And I often make the comparison with a very old TV where you have that cathode ray that scanned line by line to have an image. And now with LCD screens, by increased manufacturing processes, we can control the light of every individual pixel. So the mechanical complexity increased a lot, but by improved manufacturing processes, we were able to do so. And that's also why we can make so much transistors by manufacturing processes on a single chip. So the brain has about 85 billion neurons, and a PC advanced has 2.6 billion transistors. While the body has 800 muscles, and I couldn't find in literature how many muscle fibers we have, but it's several magnitudes of order bigger. While very complex robots have only 50 to 70 actuators. So I think we need to increase the mechanical complexity, maybe also go to modular designs, so that we have a muscle fiber which is used in a mouse and an elephant, that maybe we can go to an actuation unit which can be used for a finger, and also then if we stack a lot of them together, for example, for an elbow or, for example, a hip joint. Moreover, if one of the parts breaks, because you have that parallel design, you have redundancy, so your whole robot is still working. And also, because the forces are split over these different parallel layers, every layer can be designed very lightweight. And we also presented the idea of self-healing robotics. Here are some references, but also on our websites you will find those. Otherwise, you can ask me or the different participants from the VB. Thank you. Are there questions? I'm still available during the conference until Tuesday evening. So, except if you have questions now, please feel free to ask them. Or Tom? Yes?
It takes some time to load the springs. Can you compare with the stiff robot, how much slower it is?
Yeah, exactly. So it takes time to go to the different springs, but we think it's even an advantage, but we need to investigate it more. The reason is an electric motor typically rotates at very high speed, and you need a big reduction ratio to make it slower. So, and as Tom explained, every stage in a gearbox also consumes energy, and you have energy losses. So I think, but we still need to do the calculation that you can have more power to the output and you have less losses. But now we will compare the latest metallic SPA actuator with a comparison of a kind of equal reduction ratio, but it's not so easy to have a fair comparison. But it's indeed a good question.
I have a question about self-healing robotics. How can you embed healthy state information?
Sorry, there?
How can you embed healthy state information when something is healthy?
Yes, so it's a good question.
And how easy is to change that?
So at the moment, it doesn't know yet when it's broken, so we want to incorporate also sensors in the self-healing material to measure the health of the material. So even maybe if we can detect micro cracks before failure, complete failure crack, that we can, for example, if the robot rests and we notice some micro cracks, that we can already start the self-healing process during a healthy state. It's the same with the human body. And when we do a lot of sports, we don't have a complete injury, but we have micro cracks in our muscles, and during the night we do already this healing of our muscles. So that we also want to incorporate, but as I said, it's very new, so I think still a lot of roads are possible, but I think self-healing materials can have a huge benefit in robotics, because we cannot only make actuators from it, but imagine also a skin, a skeleton, or other robotic parts of the self-healing materials. And in the material science, this goes very fast, this development. The first paper was in 2001, and now you have already commercial applications. Although I must say the Romans, they also used stones with apparently self-healing materials. And that's apparently the reason why in Italy you still see the aqueducts, apparently. The material is very soft, but apparently those stones have also self-healing capabilities, which make them that they're still here today. So the Romans were also using very advanced materials. No more questions? Okay, thank you.
Let's take those speakers.